Linear models are very common in data analysis. I'm going to show you 3 examples to motivate the use of linear models. Here's the first one. So imagine you're Galileo in the 16th century and you want to determine how a solid object falls. You want to describe nature with a mathematical model. So you collect some data, you drop the solid object from the Tower of Pisa, and you have your assistants collect data of how far it has fallen for several different time points. Then here's the data. When you see this, it seems to motivate a quadratic formula. So you model it with this mathematical model. You can see it's a quadratic, beta 0 plus beta 1t plus beta 2t squared plus an error term, which in statistics is very commonly written with an epsilon. This signifies measurement error, and it explains why the data points aren't exactly on a parabola. Now, the reason we call this a linear model is because it can be written as a linear combination of covariates or predictors, which are represented with x's, and parameters, which are typically represented with Greek letters, beta being a very common choice. So this model can be written like this, as shown in this slide, where the xi1s represent the ti's and xi2 represent the ti squared. You can see it's the same mathematical formula that was shown earlier. Now, a next step, once we write down this model, is to figure out what the betas are. We don't know what they are. They're unknown parameters. And a very common approach to estimating the betas is to find the values that minimize the residual sums of squares. In this slide, I'm showing you the equation for the residual sums of squares. And you can see it's simply taking the difference between the data and the predicted value, and you square them and add them up. So what we want to do is we want to find the values of beta that minimize this equation. So you can think back to calculus and realize that you can do that by taking the derivatives, equaling them to 0, and solving this. But one of the things that linear models and matrix algebra permit us to do is to write down general formulas, general algorithms to find these betas generally for any linear model. That becomes very useful because, as we will see, many different data sets can be modeled with linear models. So here's another example where we can do this. Imagine you're Galton in the 19th century and you're trying to determine the relationship between father and son's heights. You're trying to determine if it's inherited and in what way it's inherited. So you collect some data and you show it here. We can again write down a mathematical model for this data. In this case, it does appear that it follows a line. It's more of a linear relationship. And we write down the model y equals beta plus beta 1x, which is a line. And we add the error term, epsilon, to describe why we see variation around this line. Now, in this case, calling the epsilon's error is a little bit confusing because what it really describes is the fact that there's natural variability around the prediction. And this could be due to the mother's height, to environmental factors, and to other unknown variables that affect your height. All right, the final example I'm showing you is one that will be very typical throughout this course, the use of linear models to represent experimental data. Here I'm showing you a very simple example where we've sampled data from 2 populations of mice, one that has received a control diet, one that has received a high-fat diet. We have 12 mice for each. We assume that they both have different average weights, and we model this with a linear model. Here we have beta 0 representing the control population mean, and we have beta 1 representing the difference between the high-fat diet population mean and the control population mean. And again, we have an error term to explain the fact that within the same population, there is variability in weight across the different mice. So in this model, we have the x1 is going to be 1 if you're a high-fat diet mouse and 0 otherwise. So it's not a line like the father's height, but it's still a linear model because we can write down our mathematical model of the data we observe with what is called a linear model, a linear combination of parameters and predictors. So we have shown you how we can use linear models to represent data for 3 relatively different examples. Now in the next few videos, we're going to describe matrix algebra, which is the language of linear models, so that you can compute and perform mathematical operations on the models that you construct.